Today we're going to be talking about Lewis structures, as it pertains to molecules and ions. A little review from College Chem, but then we're also going to add in a couple things as far as formal charge and looking at the stability of different Lewis structures. So some of these slides you really don't have anything to fill in on, and I understand that, but then some of it you're going to be doing some practice on and pausing the video and giving it a try. So Lewis theory, as far as a model, we need to realize that when we are modeling what is meant by that, let's just say water, for instance. I mean, this is a model for water. What's meant by a model is this isn't really what a water molecule looks like. I mean, it's not really an oxygen or a little, it's an oxygen, but it's not really an O. Surrounded by dots with hydrogen H's on either side in that order, with dots in between them. I mean, yes, there's electrons, but this O is representing a an atom and its inner electrons, and then these are just the valence electrons. And when we talk about a model, it's just a way to help us understand what's really going on with bonding. It doesn't make it perfect. There's other models for bonding, but Lewis model is used a lot in chemistry, the Lewis model. So as far as identifying single, double, triple bonds and where the lone pairs go, it's a pretty good model for a lot of things. There are some limitations, which we will address, to this model. That doesn't mean it's a bad model. It just means there's some issues with it when we get in some different situations. So it is one of the simplest ones. We will talk about molecular orbital theory a little bit later, but for now, this is a pretty darn good one. So it emphasizes the valence electrons to explain them. As you know, Lewis structures are the models that we end up drawing for a molecule or ion. It can also be called electron dot structures, but allows us to predict a lot of things. Stability we'll talk about today, which we didn't talk about in college chem. Shape, like tetrahedral, trigonal, pyramidal, things like that. The size of it, just be the number of atoms that we have, but then polar, nonpolar. So there's a lot of things that we'll be throwing together here, some from the past, some new stuff. So Lewis structure, as I talked about, we represent the dots as electrons around the symbol, called electron dots. But for oxygen and anything in the oxygen group, there'd be 6 dots. Let's say it's beryllium. Beryllium would only have 2 dots, but we'd put them on separate sides. Or carbon, 4 dots. We put them on separate sides to show those valence electrons. And really, those are a place for a bond to occur then. So carbon almost always makes 4 bonds. Beryllium would make 2. Oxygen almost always makes 2 bonds. And if it doesn't, it's possibly unstable. Not always, but it definitely can cause it to be unstable compared to other situations. So why do atoms bond in the first place? Well, it's a more stable configuration. It's going to be a lower potential energy. Energy is typically released when a reaction happens or bonds are made at an exothermic process. So that's a lower energy situation. So we're talking about transferring or sharing. Transferring would be an ionic compound. Sharing would be for covalent bonded molecules or ions. So the atoms obtain an outer shell with 8 electrons almost always. That's why it says usually. There are exceptions to the octet rule, but essentially most nonmetals, we're looking to get them 8 in the end of the Lewis structure at the end. There is hydrogen as an exception and a couple others, but we'll get to that in a little bit. So sharing is the way that we're going to deal with here. And shared electrons would count towards the octet. That sharing is called covalent bond. So again, we'll use water as an example a lot. So these 2 electrons can be counted for the oxygen or the hydrogen. So now oxygen has 8. Hydrogen only needs 2 because it looks like helium when it has 2. It's called the duet rule. But typically we're talking about being like a noble gas, which means that we want to have 8 for most of them, but not all of them. And we can see that here. We have bonding pairs, which are between atoms. Non-bonding pairs, also known as a lone pair, like the pair that's sitting all by itself in my room. That's called a lone pair, but those are just non-bonding electrons. They still contribute to the shape, which we'll deal with more later, but they are not bonded to any other atoms. Just a reminder of what the difference is here. So here we have pentane, this molecule. These pentane molecules are held together by covalent bonds. So if I would draw out the structure for it, be 5 carbons in a row and a bunch of hydrogens, those are covalent bonds. So it's just a quick reminder of what we're talking about here. This molecule is held together by covalent bonds. Between the molecules are called intermolecular forces. That is different. We're going to talk about intermolecular forces or attractions more later in this class. So right now we're focusing on what types of bonds are within the molecule themselves. So what type of covalent bonds? Are they single bond, double bond, triple bond, or a combination of those? Which is just a reminder of what we're talking about. We're talking about the bonds within the molecule. So a refresher of how you would do it. More electronegative atom is placed in a terminal position, but really, for the most part, we can assume that the lone atom, like again water, would be in the middle, hydrogen to the outside, because they're always terminal, they're always to the outside. Calculate the number of valence electrons. So oxygen has 6, each of the hydrogens have 1, so there's 8 total. Distribute them. I would assume a single bond always first. With bonds first, and then try to use the rest of your 8 to get everyone their octet. Always put them in as pairs. In the case of this, it works to have 8 right away with all single bonds. In the case of something like carbon monoxide, we'd have 4 plus 6, that'd be 10 electrons I need to try to figure out. Doing a single bond there doesn't work, because once I fill in 8 here, I only have 2 left for the oxygen. And the only way to make it work for both is to end up with a triple bond. So that's a quick reminder of how we're going to make Lewis structures. 6 plus 2 more, they're sharing the 6, and then this lone pair that each of them have leads to 10 total. Both the carbon and oxygen have 8, so that is where we're going to use a triple bond. So that's a quick review. I understand that from what we've done. Some of you have been, this is more recent than others. I want you to take some time. We're going to pause the video at this point, or after this little blabbage, but you're going to take some time and try to figure out the bonding with this one real quick, with all of these. So we're going to pause the video for a few minutes and then come back and check out the answers. All right, we're back. So I'm going to go through the answers on here real quick. And for instance, with HF, all we have is 8 electrons, so it's going to be single bonded. And remember, with the Lewis structure, you've got to show the lone pairs. You can put these as dots or dashes, it doesn't matter. With the HCN, we have 10 electrons, 1 plus 4 plus 5, so there'd be a lone pair here. This one already has 8, that makes 8 for nitrogen, 2 for the hydrogen. CH4, again, you can put dots as bonds, that is totally fine. I'm being a little bit time conserving here and putting dashes for a single bond. The PO4, single bond. Remember, for an ion, we want to put that in parentheses and put the charge to the outside. All these would have 3 lone pairs also. Oh, that's not showing up very well. All right, there we go. All the oxygens would have 3 lone pairs. We have a total of 32 electrons on that one. CO, shoot, I just showed you that. Forgot that was on this part of the sheet. Oh well. So there's your triple bond. XEF4 is a little new for you. If I count up all those electrons, I get 36. So what am I going to do? Because if I single bond it to all these guys, I actually have extra electrons. It's not a situation where I'm making double bonds to try to reduce the amount of electrons used. If I put 2 on each of these, I'm going to end up with extra electrons. So this is possible. Xenon, some other noble gases can make bonds, but it'd have to be the heavier noble gases. But it is possible. We see this sometimes. That's 28. Or actually, that's 32. I'm sorry. So there's 4 electrons left. And whenever there's extra electrons, so if we're low on electrons like we were here, that's where we make double or triple bonds. Now there's extra electrons. I'm going to put them on the central atom. So those lone pairs will go on the central atom. So we're now going to have something that we haven't seen before in college chem, and that's where there's 6 pairs of electrons around the central atom, but only 4 are bonding. 2 of them are lone pairs. We'll deal with that shape later, but that is a new situation for us. Moving on. a reminder from College Chem, resonance can occur when you are kind of a multiple bonds or lone pairs where you really are deciding where that double bond goes. In reality, this is not a double or a single bond, but this is a limitation to the Lewis model. We don't have a better way to deal with this. In reality, when measured, this bond, when measured, is 1.5 the length, or it's a length of like a 1.5 bond. This is a certain length. A single bond, a double bond is a certain length. If you'd average the length of a single and a double, that's actually what each of these are. But we don't really have another way of dealing with that, so this is our best way of dealing with that with this model. So it is a limitation to the model, resonance is, but this is how we deal with it. We show all the possibilities. So just something from College Chem again that we did on the next slide. CO3. We have, here's one, and all the others would be a double bond here, but I'm going to draw in all these electrons real quick. So there's only 24 electrons to work with CO3. So we would need one double bond, but that's it. So what is truly happening here is all three of these bonds are identical. None of them are single bonds or double bonds, but they're in between a single and a double. If I would average them, and I'm totally don't have these numbers on me. Actually, I do on the next page. I wasn't paying attention. So they all have identical bond lengths of 136 picometers. So why is that? Well, I have two single bonds, so that's 143, 143, and then add that to a double bond, 123. Add all those up. I've got a 9, I've got a 0, I've got a 4. Ooh, that looks like some good cleaning solution. If I divide that by 3, I take the average of that, that will give me about 136, I think. Really, I probably should have done that before. So here's a 1, there's a 3, that's a 1, that's a 0, there's a 3, there's a 9, 19, and sure enough, it's about 136. So I'm averaging the two singles and a double gives me the length of all of them at 136. Sometimes I just am not as prepared as I thought I was. So here's, so I moved on to that next one already. Looks like I have length spelled wrong. Sorry about that. Pet peeve of my own, and I just violated that one. So here is some Lewis structures practice. I want you and your people to think about this one. Which one do you think has the shortest to the longest nitrogen-oxygen bond? So like this first one here, it exists like this is what it's saying. So that's going to be a single bond between nitrogen and oxygen. There'd be a lone pair here too, but there's a single bond there. So I'm going to pause the video now. I want you to pause the video and try to figure out the Lewis structure of the rest of these, and then from that determine which one's the shortest bond and which one's the longest. By the way, triple bonds are the shortest, single bonds are the longest, and then anywhere in between that spectrum. So I want you to pause it and then try it. And once you're pretty much done, go ahead and press play, and we'll see what you got. So I'm back, and I'm going to show you what I got here. I'm just going to write the valence electrons above each of these for my own. This really should be in brackets. Both these should be in brackets, but all these ions should be in brackets, but that's okay at this point. So I'm just going to, or just for this purpose, I'm going to show what I got on that one. Here we have NO triple bond. Yes, there's electrons here. I didn't fill any electrons here either. I'm really focusing on what the bond type is here. With this guy, we have here, and yes, there's a lone pair, and there's other lone pairs, but I really want to see that there's a single and a double. And the last one here, there's a single, another single, and then one double. And yes, it's in brackets, but I'm more concerned about the types of bonds going on here. So the longest bond would be this guy right here. So this is from order to shortest to longest. Since there's 5 of them, I'm going to label this as the longest bond. The triple bond would be the shortest. So I'm going to go number 1 on that guy. A combination, I have single and double combined And if I did some averaging and got some numbers, I could actually figure it out. But these are double only, so that's going to be the next shortest. Then this guy is going to be number 3 because it would be the average of a single and a double, where this would be an average of 2 doubles, or 2 singles and a double. So this would be the next longest. It wouldn't be the longest, but this would be the longest. So that is, there's a lot going on there too, as far as, but most of that is things we've seen before. The new topic here is called formal charge, and this is a way to identify some structures that are more stable than other structures. So formal charge, how you figure it out is you take the number of valence electrons and subtract it from the number of electrons in the Lewis structure. If they're non-bonding or lone pairs, they count as for that atom, but then they get half of the bonding ones. The sum of the formal charges in a molecule are going to equal 0, kind of like oxidation numbers, that in an ion, the formal charge will equal the charge. But this is going to help us compare one to another. So here in this chart, you can see that hydrogen has 1 valence electron. And so when I look at the valence electrons, I just want to identify it from the periodic table. 1 for hydrogen, 4 for carbon, 5 for nitrogen. Same thing for both of these. So it's looking at the 2 ways of organizing this HCN. What if we put the N in the middle instead of the C? In this situation, there's no bonding, or there's no lone pairs for the hydrogen and carbon, so that's why there's 0 there. Here the nitrogen has this 1 lone pair, so that's why there's a 2 there. Same idea here, the carbon has the lone pair, that's why there's a 2 here. But then carbon, or the hydrogen here, is getting half of this pair. So I would assign it a 1. I think of it as not half of 2, but I do a 1. So 1 minus 1 gets a 0. This carbon has a triple bond and a single bond, so there's really 8 shared, but it's going to get half of those. So 4 minus 4 equals 0. This nitrogen has a triple bond here, so it's 3. So there's really 5 minus 5 equals 0. So the formal charge of all of the atoms is 0. In this structure, the formal charge of nitrogen is a plus 1, because there's really only 3 triple bonds, single bonds, so it's half of the 8 shared, so it gets 4 of them, so it gets a plus 1. The carbon has 4 minus 5, so it ends up getting a minus 1. So this is the more stable one. The formal charge is closest to 0 is the more stable structure. Is this possible? Yeah, it's possible, but it's not as stable and not as likely because of that. So this one was done up here. I want you to try to assign formal charges to the rest of these on the bottom. So press pause and give that a try. So now we're back. I'm going to draw in this real quick, because we do need these valence electrons. I don't know if I'll do this for all of them. The other ones are all single bonded, but I'll just go this way. So in this case, hydrogen has 1 valence electron and it's sharing a single bond. So 1 minus 1, and hydrogen would have a formal charge of 0. Fluorine has 7 valence electrons. So 7 minus 2, 4, 6, plus 1 half of the bond. 7 minus 7 is 0. So that's a stable situation. Same idea here. Carbon has 4 valence electrons. It gets half of these bonding electrons, so that's a 0. Hydrogen has 1 valence electron, half of the bond, 0. So all these are formal charges of 0 so far. PO4, let's just look at one of them to understand this. So O, like this. So P has 5 valence electrons, 5, minus half of all these bonds. So they're all single bonds. There's 4 single bonds, so it'd get half of those electrons. 1, 2, 3, 4. So P is a positive 1. The oxygen, 6 valence electrons. Oh, I'm making a mess now. The oxygen is 6 valence electrons minus what it is in a structure. 2, 4, 6. Half of that, 7. So that's a minus 1 for each of the oxygens. Carbon in this case, there's a lone pair, is going to be 4 minus, gets half of these, 3, 5. So it's a minus 1. Oxygen is going to be 6 minus 5 also, so that's a positive 1. XeF4, I'm going to write out real quick. I'll just look at each. I'm going to look at one part of it quick. So the Xe has 4 bonds. So if I look at the Xe, there's 7 valence electrons. It has 4 in the lone pairs plus 4 more shared. So there's 8. So that's a -1. The fluorine is 7 minus 7. That's a 0. I feel like I did something wrong. So the xenon has, it has 8. That's my wrongness. Oopie. 8 minus 8, which equals 0. So it has 8 to start with. I was thinking 7. So let's look at an application to this. Some of you may have seen Breaking Bad, and if you have not, that's okay. But I'm going to show you an application real quick of this different situations having different stability. So there is an ion called the cyanate ion. The fulminate ion, just going to show the double bonds, is not as stable. It's unstable. -1, -1. So if I do the formal charge of this one, it's 6 minus 6, which is equal to 0. This one is 4 minus 4, which is equal to 0. This one is 5 minus 6, which is equal to -1, equals to -1. Okay? If I do this carbon, 4 minus 6 minus 2 for a formal charge. This one is 5 minus 4. That's a +1. And this is 6 minus 6 for a 0. These are closer to 0. That's what makes this one a more stable arrangement. More stable arrangement can be an explanation of why some things are very reactive. It's referenced down here to Breaking Bad Mythbusters. There is a clip in that show where mercury fulminate is used and just thrown onto the ground, and a large explosion is made, and Mythbusters looks into the possibility of something being that explosive. Yes, it's unstable, but is it that explosive? So it's an interesting little application to see how real the science really is in that series, not really a movie. Last few things here. There are some exceptions to the octet rule. We've talked about that in college chem a little bit. We didn't really talk about the odd number issue. For instance, nitrogen and oxygen. Nitrogen has 5, oxygen has 6. There's 11 electrons. What do you do with that? Let's say we have a double bond. There's 6, there's 6. There's 8. Here's 10. We could put the lone electron on the nitrogen, but that doesn't give them both 8. It's called a free radical. Because of that, very reactive. This is a substance that is produced as a pollutant. It immediately joins with an oxygen in the air and forms NO2. That's also is a free radical, which then joins with water quickly to make some nitric acid. So very reactive, but it is a possibility. It's kind of it's a limitation to the Lewis model of bonding. And we know there's going to be some incomplete octets, like boron's good with 6, that makes it stable. And in fact, in college chem, we talked about phosphorus and sulfur making 10 or 12 electrons if things are bonded to it. 5 or 6 things like hydrogens or halogens be bonded to it. But in reality, anything from the third period down that is a non-metal, this could happen. So third period and lower, any of those could have an expanded octet, with some of them being in d orbitals. So that is it for Lewis structures and formal charge.